In our last video, we discussed about how we can see on a graph how a function is changing and describe that by being increasing, decreasing, or constant. Right? We said that an increasing function is one that goes up as we move from left to right. So goes up, looking left to right. We said that a decreasing function is one that goes down, looking left to right, so goes down, looking left to right. And that a constant function is one that stays constant, right? That doesn't change. Or maybe say it stays flat. But this only tells part of the story too, right? There's a lot more nuance that can be discussed here as well, right? Is this kind of increasing function the same as this kind of increasing function, right? There's some level of steepness that we want to account for there too. Or is this type of decreasing function the same as this type of decreasing function? Now, there is a whole big study dedicated just to talking about how functions change over time, what their rate of change is. And in fact, that's one of the big ideas of a calculus course. For now, though, at least, we can explore a little bit about how this works with linear functions, with lines. And that'll be a good enough place to get us started in a pre-calculus class to then explore this in much, much more detail when we get to a calculus course. But at least with lines for now, we can be more specific about this. We can in fact quantify just how much our function is increasing or just how much our function is decreasing over time. And this idea is called the function slope. And sort of informally, the slope is just a measure of a line's steepness. Or how high does it slant up, or how flat does it stay, or how far does it slant down, or how slowly does it slant down. We can define and quantify this a little bit more formally, of course, too. And so we'll say that the slope of a line through distinct points x1 and y1, here we're just labeling x1 and y1 to signify some arbitrary x and y coordinate, and to distinguish that from our second point, which we'll label x2 and y2. So the slope of a line through distinct points x1, y1, and x2, y2 is defined as the rise over the run, or in other words, the change in y over the change in x, which we can similarly write with this symbol here, right? And I'll just note this symbol here, this delta symbol, this is called delta, and can be read as change in. And so we can write delta y over delta x. Or in other words as well, we could say the difference between the y coordinates of our two distinct points divided by the difference between the x coordinates of our distinct points. And as usual, since we can't divide by 0, this would be where x2 is distinct from x1. But what is all this rise, run, change in y, change in x stuff all about anyways? Well, let's look at a picture and let's see how it works. Let's say this was our x-axis and this was our y-axis, and we had two distinct points with a line running through them, and perhaps we call this point here x1 and this point here x2, and thus this point here y2 and this point here y1, right? So this has the coordinate x1 and y1, and this has the coordinate x2 and y2. When we talk about the rise or the change in y, what we're really saying is the difference between y2 and y1. In other words, how high are we rising up when we go from one point to another, right? What is the difference between this level where we're starting at y1 and this level here where we're ending at y2, right? So how much are we going up this way, right? And this would be what we call our rise, or y2 minus y1. Likewise, our run is how much are we running over, right? From our initial x1 point to our new x2 point, how much are we sliding over horizontally? That's the difference between here and here, or in other words, this distance here, which we call our run, or x2 minus x1. And what the slope does is it describes the ratio of how much we go up divided by how much we go over. So if we're going up a lot more, our slope is going to be a lot higher. If we're going over a lot more, we're dividing by a bigger number, and so our slope is going to be smaller. Additionally, anytime we have an increasing function, our rise is going to be greater than 0. In other words, our difference between y2 and y1 is greater than 0, which means that when we have an increasing function, we're going to have a positive slope. And so this here represents the graph of a positive slope. On the other hand, if we were to draw something like this, our rise is going to be less than 0, right? Our y2, our value down here maybe compared to our y1 up here, is going to be smaller. So the difference between those two is going to be negative. y2 minus y1 will be negative. And so when we have a decreasing function, that's going to tell us that we have a negative slope. But as you might guess, thinking back to our increasing, decreasing, and constant functions, these are not the only cases. We could have something that looks kind of like this, where our y1 and y2 are exactly the same, right? So in here, we're not rising up at all. The rise is equal to 0, right? Rise is equal to 0, or the difference between y2 and y1 is equal to 0. In other words, whenever we have a constant function is going to imply that we have no slope, or a 0 slope. The slope is equal to 0. But even this isn't really quite the end of the story either, right? We could be going up from left to right. We could be going down from left to right. We could be flat from left to right. But also, what if instead of being horizontal, we were just straight up and down vertical? What if we just had something like this? Well, this is an interesting case because think about what it means to be our slope. Our slope is the rise over the run, or the change in y over the change in x. Well, what's the change in x in this case? We're not really changing x, right? We're just staying on this single x value here. And so because we're just staying on that single x value there, the difference between any two x values for this line is just going to be 0. Since we can't divide by 0 and that delta x, that change in x, is sitting in our denominator, we don't really have any way to define slope for a straight up and down vertical line. And because we don't have any way to define it, we're just going to say the slope is undefined. But now we said that slope is a measure of steepness, and it's going to help us kind of distinguish between measuring lines that go up really, really fast, that are very slanted, versus lines that creep up really, really slow, that are more closer to flat. And so how do we actually compute that measure? How do we actually get a value for slope? Well, let's look at an example. Here we want to find the slope of a line passing through the points -3, 4, and 1, 2. In order to calculate a slope, all you need is 2 points on a given line, and any line can be defined just by 2 points, so this works out really nicely for us. Now, to do this, all we really have to do is remember that our slope is equal to the rise over the run, or in other words, y2 minus y1 divided by x2 minus x1. Now you might be saying, well, what is y2, what's y1, what's x2, what's x1? Well, we can just pick either of these coordinates, maybe call this one 0.1, this one 0.2, and label those points accordingly. 0.1 and 1 and 2 are 0.1 and 2 are 0.2. And 1 and 2 are 0.1 and 2 are 0.2. And 1 and 2 are 0.1 and 2 are 0.2. And 1 and 2 are 0.2 and 1 and 2 are 0.2. And 1 and 2 are 0.1 and 2 are 0.2. And 1 and 2 are 0.1 and 2 are 0.2. And 1 and 2 are 0.2 and 1 and 2 are 0.2. And 1 and 2 are 0.2 and 1 and 2 are 0.2. And 1 and 2 are 0.2 and 1 and 2 are 0.2. And 1 and 2 are 0.2 and 1 and 2 are 0.2. And 1 and 2 are 0.2 and 1 and 2 are 0.2. And 1 and 2 are 0.2 and 1 and 2 are 0.2. And 1 and 2 are 0.2 and 1 and 2 are 0.2. And 1 and 2 are So maybe let's pick this one here and call this one x1 and y1, and this one here to call it x2 and y2. Now, of course, you might ask, well, why did you pick -3, 4 to be number 1 and 1, 2 to be number 2? What happens if we switched it? There's no need to worry. It actually won't change the answer. Now, I'm going to work it out this way. I would encourage you, if you are watching at home, to work it out the other way where you flip them around. Label the point 1, 2 as x1, y1 and the point -3, 4 as x2, y2, and see that you actually get the same answer as well. But once we've labeled these here, all that's really left for us to do is to plug in. And so y2 is going to be 2, and so we'll plug that in here. y1 is going to be 4, and so we'll do -4 divided by x2, which is 1, minus x1, which is -3. Now I'm going to be careful with my parentheses here and make sure I put the quantity -3, so I know that we're doing 1 minus -3 rather than just 1 minus 3. But once we have that, all that's left to do is to do the arithmetic. And so if we do 2 minus 4, that's going to give us -2. And if we do 1 minus -3, that's going to be the same as 1 plus 3, or in other words, -2 over 4, which we can simplify to -1/2. And this would be our final answer. And so in this case, we're able to quantify the slope, quantify the steepness of the line that runs between those 2 points, and that value happens to be -1/2. This describes, again, the ratio of how much we're going up relative to how much we're going over, right? And so in this case, what this would mean is for every 2 units we move over, so for every 2 units we move left, we move 1 unit down. And I'm saying down specifically because it is negative. If this was positive, it would be up. But I think we'll stop here for now. It's pretty powerful stuff when we can start to use tools from math to describe things that we see visually on a graph or things that we experience in the real world. Next time you're driving up a really steep hill on a car or driving down a really steep hill in your car, you can think about what the quantity of the slope might be. How might you measure just how steep of a climb or just how steep of a descent that really is? Anyways, I hope you found this one helpful. I'm looking forward to exploring the details of linear functions a little bit more with you in the next couple videos, but otherwise, I hope you have a great rest of your day.